Well, let me give you some background of this presentation. Actually, in this building, and I'm going to conduct some wind and environment vibration and study. Last year, in 2013, on February 7th, the Shanghai Information and Building had a strong vibration on this day, and which caused the staff inside the building's emergency evacuation. So as you can see from this slide, so why people felt a vibration? And people conducted some analysis and tests to the possible reasons of this vibration. It might be an earthquake. And so generally speaking, the vibration of the building can be caused by many factors. In addition, we also conducted some analysis to some other possible reasons, and for example, some other vibration and sources. And for example, structures and vibration, and the wind and surrounding construction machinery vibration. So, and basically, so actually, and so actually there was a subway line beneath this building. And so, people are also considering, are there any additional work which are causing the vibration in this building?
Another thing is that I'm going to talk about the wind-induced force that will affect the building. Why do we concern about the wind? I'm going backwards a little bit because, well, our building is in the center of the Lujiazui area. And also, you can see surrounded that building, we have a lot of high-rises as well. We are very close to Shanghai Tower.
200米以上的超高层的一个密集的一个区域内，那么应该讲呢，这个风的一个情况呢还是比较紊乱的。那么整个大楼的一个情况呢，是地上呢是41层，地下呢是4层。那么总个高度呢，建筑高度呢是184米，那么上面还有一个90米高的一个通讯的一个铁塔。那么通过我刚才前面介绍了几个方面的一个是地震的情况呢，我们对于那个上海地震局啊各方面的一个有记录的地方去调查了一下呢，这天呢是没有发生地震。那么还有一个呢，就是对于那个大楼的前面的一个地铁2号线的运行状况是怎么样？那么应该讲呢，也是一个非常也没有出现一个不正常的运行情况。那么余下的一个我们比较关注的就是一个风的一个情况。那么当天的一个气象记录情况呢，也是只有风也不大，只有7级。那么风速在大概在13到17这样一个每秒米这样子一个情况。那么应该讲也是属于一个我们的原来设计的一个范围内，是一个正常的一个不大的一个风。那么我们针对这个风的。
So based on the analysis of the wind, you can see that's the survey for the wind for over 1 year.
So, and this is background. We could see this is the typical and meteorological year and hourly and the mean wind speed in the Shanghai area. And we should say that, and usually the wind goes in south and eastern direction in Shanghai. The building has been built for more than 10 years and has been running smoothly and without any major problems. and neither of the past typhoons and had a positive hit in Shanghai, and the wind velocity and profile typhoon that passed Shanghai is different and from the boundary and the layer and wind profile, and is also different and from the past Fujian and Zhejiang area. And so this is about background of Shanghai. In addition, in this area, we should say in Lujiazui area, and is a urban area and with a big building density, and height and surface roughness and category and is class D. The wind and profile index and maintains 0.3, and usually in this area. And focusing on this issue, and we conducted some research and contents. The first test is on the field measurement, and the second test is the numerical and wind and tunnel. And actually, we have been conducting this field and measurement and since at that time until today. And by recording the relevant data, we could conduct more and the relativity study for that. So far, we haven't detected any major phenomena. So everything remains normal. The second test we conducted was the numerical and wind tunnel test. So these are some of the field and measurement. The long-term monitoring of the wind and field characteristics around building. So in real-time and monitoring and wind speed and the direction data around building to get wind field characteristics, and through nanometers and decorated 20-meter and 40-meter high up the tower. So these are some of the bidirection accelerator and to monitor the relevant vibration. Actually, it's not only used to detect the wind vibration. Of course, we try to find out more and possible and risk factors. So these are some of the wind speed monitor on top of the building. And one is the mechanical monitor. The other one is the ultrasonic monitor. And actually, this is a accelerating monitor. And based on a large number of long-term monitoring data, actually is the data collected from a few months, and which is not very much related to wind. So, we were able to record the relevant information and from subway and from other factors. So this is not the data from the whole year. And this is about the field measurement on the wind speed from September last year and to October last year. And we detected the maximum instantaneous wind speed and reached level 9, even to 10. So, the PSD and the function of the maximum and wind velocity is like this. And the power spectral density of the wind velocity obtained by measure and is higher than ruled and by cause, it shows that the actual wind field is different. In terms of turbulence in 3 directions and R 0.22, 0.18, 0.17. And as a matter of fact, these data are not taken from the whole year, so it does not make much sense. Comparison with the observed data of the wind and speed recorded at weather stations. And the weather station records a maximum wind speed for 4, 2, and 5 levels. And the measure results and show the maximum wind speed for level 7 and gusts of 9 level. According to the field characteristics of Lujiazui area, the measured results of the weather stations and can get a maximum and wind speed of level 6, and which about level 1 above the weather history data. So, generally speaking, during the course of monitoring, and no obvious vortex-induced vibration detected. So this is about the detection on the field. Let me show you this wind tunnel the test we conducted. Actually, this is the theme of my presentation. So, based on our study, we try to simulate the situation of that day. And based on the video recording, and we saw, actually, there's a tower on top of the building, and it was vibrating and pretty much to a high level, especially to the horizontal level. Therefore, we plan to conduct some simulation to repair the situation of that day. So, the unsteady and wind load and time history data is directly loaded into the infinite element model to calculate the wind vibration response of the structure. And this is the numerical wind tunnel. And so this is the building we are working on.
So this is our simulation, and also we have modeling other high-rises around that building. And also we have considered 8 different wind directions. And also everything is compliant with the code. The 50 years return period wind pressure is 0.55 kilopascal. And also the roughness coefficient is 0.3. That's compliant to the Chinese code and standards. So this is from our lab simulation. So the length is 8 kilometers, the height is 3 kilometers, and the width is 6 kilometers. So this is the dimension for the wind tunnel. And the inlet wind, according to different height, we have 5,363 wind, fluctuating wind. And to simulate the actual situation. So the sampling time step is 0.1 second. And we have 1,200 steps. So, which means in 120 seconds, it's enough to capture the fluctuating wind characteristics and wind speed information for a long period of time. So, you can see on the right side that this is the diagram that we captured. This is the wind speed profile. In terms of different height, we have different analysis. And also we compare our results with the Chinese code. Frankly speaking, actually all the data we captured are ideal data, and actually it's close to the Chinese code. The reason why we have this analysis is because we want to understand when the building is facing the wind from different directions, what is the vortex shedding? So in different wind speed, in different wind directions, we try to capture the data. You can see on the right corner side, we have different wind angles, wind directions, and then we capture the results in terms of different wind velocity. So that's the data we captured. And this different diagram and picture shows that because our building is located in the center of a lot of other high rises, so the surrounding wind field it's very complicated. So you can see that the wind is actually not constant, so it's very complicated from different directions. So these are our simulation. And also we have analyzed the structural introduction, but we'll skip this part because it's not that relevant to our topic today. So I will go through more details about the wind. So basically, after we modeling our structure, you can see that the first 3 order natural vibration period of the building is 3.36 seconds, 2.04 seconds, 1.58 seconds. If we are only going to consider the building, the structure excludes the towers above, we also have our data as well. So the steel tower above actually is only accounts for 0.5% of the total tower structure mass. So based on analysis, based on our research, you can see in 0 degree wind angle, and when the wind velocity is 20 meters per second, the frequency is actually 0.47. In the second tier, it is 0.48. And it's very close. That's how we're trying to simulate the situation at that specific period, at that date when the accident was happening. So our analysis is that the second order mode, the frequency is very close. So when the wind velocity is around 20 meters per second, the vibration frequency is very close to the structure's vibration frequency. So it will affect the structure and cause the vibration of the building. And also this is the structural displacement response analysis. The red line means the frequency we just saw, which is the structural vibration frequency, 0.48. So you can see that at 0 degree wind angle, it's very close. So which means that our result is correct. And then this is the displacement's time histories on the top of the tower under 0 degree wind direction. So you can see across wind, even the displacement is minimal, but the vibration is very huge. So that's where we are trying to understand whether this vibration will lead to the accident, leads to the incident. This is the acceleration analysis of the crosswind. There's a mistake here. It should be vice versa. So based on our research and analysis, so we have conclusions. First, it's in terms of the architecture, in terms of the building itself, in different wind angle situation, in different wind velocity situation, when the structure, when the building so our topic is actually trying to find out in what wind angle, in what wind velocity that the building will be affected. So our result shows that at 0 wind angle and at the speed of 20 meters per second, we found out that our building will be affected by the wind. And there was also another mistake on the PowerPoint. It should be second order rather than the third order. So our structural engineer, when we're trying to design this type of buildings, when we have a steel tower on top of the building, so we need to consider the vortex-induced vibration and the whipping effect. If the building will be greatly affected by the wind, the building will be heavily damaged and affected, which will lead to the accident we just seen for this building. So we need to make sure that when our structural engineer was trying to design our building, we will make our structure strong enough. And at the same time, actually, for the building we analyzed, 0 degree happens to be southwest angle, and for Shanghai, most of the wind actually come from southeast. So southwest wind is actually a low frequency accident or event. And also, at the beginning, actually I forgot to mention one thing. Actually, at the time that when we have that accident, based on the meteorological station's data, actually that wind was not come from southwest, but the wind may change its angle because you see that surrounded that building we have a lot of other high rises which will affect the wind direction. So the wind angle, when it hits the building, it will be a lot different. So that's what I'm trying to say. Thank you.